Okay, so thank you very much, and thanks to the organizers for giving me the opportunity to speak here about the emergence of heavy tails in stochastic gradient descent. And I should also say that this is joint work with Shizhen Jiao from Northwestern Polytechnic University in China. And he also wanted to come here, but he couldn't get his visa in time, so he's not yet delivered. He wants to. Okay. Yeah. Okay. So at the beginning of my talk, I will repeat some basics that you have now in many other talks on stochastic gradient descent and its role in deep learning. Then I will talk about continuous time approximation for stochastic gradient descent. And then I will let the continuous time approximation that we are using here, which is homogenized stochastic gradient descent. And then I will show that also in this continuous time approximation, even though we are not using any linear processes, jump processes, we are seeing the emergence of heavy tails, and I think we can give some quantitative results on the tail behavior of the distribution of parameters in this case. And I conclude my talk with some numerical experiments. Okay, and so as you have seen in many talks, the backbone of deep learning really is the empirical risk minimization. So we are given some loss functions, could be quadratic loss, cross entropy loss, and so on. We have some statistical learning model like a neural network, or also a much simpler model like linear regression, and parameterized by some parameter vector, typically high-dimensional parameter vector, which here would be called x. So x is here the parameter vector, which we want to determine. And we do this by minimizing the empirical loss, the average loss on our training data. And our training data consists here of our feature vectors AI and our labels or responses BI. Now, and here we're mainly talking about really the risk minimization on the training data, not about generalization, even though it's a very interesting topic, of course, then how this generalizes to our testing data. And this generalization either is kind of achieved with the minimization method. So we have already heard that stochastic gradient descent seems to have this intrinsic probability of allowing good generalization, or it could also be defined the loss function by adding some regularization what we are. And the basic optimization algorithm that is used, mostly not in this simple form, but variants including like adaptive learning rates, batch normalization, momentum, and so on. But all these methods are still built on the very basic idea of stochastic gradient descent. So we are updating our parameter xk by following the direction of steepest descent, but not taking the full gradient of our loss function, but instead sampling from our training data. Take the sample size B. B is the batch size, and our training sample is called the batch. And there are different ways, of course, of sampling here, but it is a random subsample. And this is how stochastic gradient descent works. And the important parameter here is, of course, the learning rate gamma, which on the one hand side, you want to choose it large such that so you're getting a significant update of your parameter vector. But on the other hand, you don't want to set it too large because then your method might not converge to something. Yeah? So there's an inverse trade-off here in the program. And one way of looking at this stochastic gradient descent is to view it as a noisy perturbation of gradient descent. Yeah, so and when you see it from this perspective, you introduce the gradient noise. Yeah, so here this is the gradient noise, basically the difference between the gradient coming from your batch and the full gradient. And it is easy to see that this noise is unbiased, so expectation is 0. So the interesting feature is its covariance index, which here we denote by C. And then when you formulate like this, you see that the gradient descent perturbed by this gradient noise here with the scaling factor of gamma. And already here, so in particular, if you now simplified a bit by choosing a quadratic loss function linear model, then f will be quadratic and the gradient of f will be linear, and you will get something that is a linear random recurrence relation. And in the very influential paper here on the Heavy-tail phenomenon in stochastic gradient descent, Yunus Balaban, Shimshekli, and Shube studied this linear random recurrence and obtained some very interesting results on the convergence here, the convergence rate of this recurrent to equilibrium. And in particular, they studied distributional properties and showed that the stationary distribution of this random recurrence will have heavy tails. Yeah, and this is kind of what now connects stochastic gradient descent with heavy tail random products. And also from the empirical side, there is good support here for the appearance of heavy tails in the distribution of iterates of stochastic gradient descent. So here this is taken also from a very well-known paper by Hodgkinson and Mahoney, where they look at, well, here it is the norm of the increments of stochastic gradient descent, which of course is also related to the norm here of the stationary distribution, because it will give you a lower bound in the sense. So if this is heavy tail, also the other one has to be heavy tail. And they did maximum likelihood estimate of the tail exponent. And here you see some histogram, and clearly this is far from Gaussian, could be a power law. And if you estimate the tail exponent, you see here that values going from 6 down to 1.5. And this is here with increasing number of parameters. So you can also see that as the dimension grows, as the size of the parameter vector grows, the tails get heavier and heavier. And just also to fix terminology, I mean, this is something I think one doesn't have to explain here, but what do we mean exactly by heavy tails? So heavy tail means that the tails of the distribution decay slower than any exponential function. But here, typically, we will not talk about one-dimensional distributions. We will talk about RP-valued random vectors, and such a vector is called heavy tail if we can find any direction u in which the projection utx is heavy tailed. And if we want to quantify the decay of the tail a bit more, then it's a useful tool to look at the tail index. And the tail index eta is defined in such a way, so it's simply the largest p such that the pth moment of our random vector is still defined. And in particular, if the tail index is finite, this already implies the heavy tailness of x, and smaller tail index then means heavier tails. Yeah. And for example, if the tail index is smaller than 2, then we already know that not even the variance is existing of our random vector. And here, typically, we would work with not just marginal distributions, but with stochastic processes. If we know that our stochastic process converges to a stationary distribution, we can then look at the tail index of the stationary distributions, but sometimes we cannot show that we have convergence to a stationary distribution. Then it's useful to still talk about the asymptotic tail index, which is defined as the tail index, but here we're using the limiting behavior of the model. So we look at the limit behavior of the pth moment of our stochastic process.
Would it be just expectation of the limit if we have uniform integrability?
You cannot, without further conditions, you cannot exchange.
But but uniform integrability gives you.
The nice situation is you know that it converges to a stationary distribution and it's uniformly integrable. You exchange it's the same, but in cases where we cannot show this, we can still look at the asymptotic gradient. And then, of course, in the end, the justification will be in numerical empirical results. So, because what you do when you look at stochastic gradient descent, you're looking at finite time anyway. You have a finite sample.
But in that case, you may not have a target distribution, a limiting distribution.
Yes, but it still tells you something about the behavior of moments. It tells you that some moments will explode, some moments will converge. And when you have convergence and uniform integrability, then you have a statement about the tail index of the asymptotic distribution.
Sure, but
But the asymptotic distribution is something you will never observe anyway in stochastic gradient descent. So you will only observe pre-asymptotics. And also you're always estimating for a finite sample, strictly speaking, in your empirical data, you cannot have hidden tails anyway. So having an exploding moment is almost the same as having a
Sure, but there is the counter argument that says if I can prove that there is a limiting distribution of a fixed target, so then when I run things for n steps, I can compare how far I'm from that target. Yeah, so then.
In nice cases, we can also do this, then we give you a convergence rate to the stationary distribution, but we also want to make statements when we cannot show those distributions. Okay, so the next step is now to look at continuous time approximation for stochastic gradient descent. And the first question you could ask is, why do we need this continuous time approximation at all? Because as I've shown you, you can obtain results directly from looking at this stochastic recurrence relation. But then again, typically, continuous time models are more tractable, and you have more tools to work with them. You have differential calculus or stochastic calculus, and they're more tractable, and typically you will obtain stronger results or more explicit results when you look at continuous time. And also, as we have seen in some of the other talks, then these models only serve just as the starting point of then other questions on the behavior of stochastic gradient descent, optimal initialization or escape from local minima and so on. And there it's always nice to have a more tractable model that you can work with. And this is given by these continuous time approximations of stochastic gradient descent. And here again, one way to do this is to use a diffusion approximation. And the idea is that you take your stochastic gradient descent and you replace the gradient noise here by IID Gaussian variables with matching covariance. And then this looks, or this is the Euler-Maruyama discretization of an SDE. And under suitable scaling, this converges then to a stochastic differential equation like this. Yeah. But what people usually do, they do a Fourier approximation here of the covariance matrix. And they say, well, we just replace this covariance matrix here by a constant matrix, or even just a constant multiple of identity. And then what you get is the so-called Langevin approximation or overdamped Langevin equation, Ornstein-Uhlenbeck process, and which looks like this. No? And then, of course, this is a Gaussian process. Stationary distribution is also Gaussian, and you do not get heavy tails. Yeah? So with this model, you cannot reproduce this phenomenon of heavy tails in stochastic gradient. And therefore, the usual argument is that you should not do this diffusion approximation. You should not use here normally distributed gradient noise, but instead you should use a non-Gaussian approximation. Now, the arguments are here again, the influential paper here is this paper by Shimshekti, Saum, and Skubus Palaban, where they argue that, well, again, looking at the expression for the gradient noise, you have a sum of IID random variables. If batch size is large, then you can invoke a central limit theorem. If variance is finite, you get Gaussian, but if variance is infinite, you get a generalized central limit theorem, and this gives you an alpha stable distribution. And therefore, they propose to not use Gaussian noise, but instead alpha stable noise here. And then with a constant here in front of here, so losing the state dependence, and then under suitable rescaling, we get this Lewy-driven Ornstein-Uhlenbeck process, where now you are using alpha stable noise here locally, but also in the limit you get an alpha stable invariant distribution, and you obtain heavy tails. But so this is of course a very nice model that has led to many interesting consequences. But let me also offer here some critical points. So first of all, in order to invoke your central limit theorem, you need a large batch size. But typically, empirically, batch size doesn't have to be large. So even if you choose batch size equal to 1, you will observe heavy tails. And to the contrary, what you're observing is if you increase batch size, then the tails get lighter and lighter and closer to Gaussian. So the heaviest tails you obtain with smaller batch sizes. Yeah? And this is actually the opposite what is claimed here. So second thing is that with alpha stable distribution either has finite variance, then it's Gaussian, or it has infinite variance, and then it has very heavy tails. But you can never obtain like medium heavy tails with a tail index larger than 2. You can never get it with an alpha stable distribution. Yeah, even though if you just estimate your tail index, as you've seen before, you also observe values larger than 2. Okay. So let me sum up what we have seen here. So in the Langevin approximation, you use locally Gaussian gradient noise, but also globally you obtain Gaussian parameter distribution, no heavy weight. In the alpha stable approximation, you assume locally non-Gaussian noise. So your gradient noise is locally non-Gaussian. So locally always mean conditionally on the current state of gradient, stochastic gradient descent. And also globally, you get a non-Gaussian parameter distribution. But now the model that we will be looking at, homogenized stochastic gradient descent, is kind of a combination of these two, because here our gradient noise locally will still be Gaussian, but because it is state dependent, it will globally lead to a non-Gaussian parameter distribution. Yeah, so you can still have locally Gaussian noise, but globally your parameter distribution will be indexed.
Can I just clarify something, because this is very nice, but what I see here is really you have the wrong scaling when you see the stochastic gradient descent with this additional noise, that difference between the new coefficient with the band size and the gradient, right? You have the wrong scaling, and somehow in order to fix the scaling, you absorb into the diffusion coefficient, let's say, the step size. So if we go back one slide, it will be obvious that if I set alpha equal to 2, I'm thinking now the very simple Gaussian case, I have Brownian motion, right? So the first one, it will be gamma to 1/2, which is the right scaling for the diffusion, diffusive part. But then the diffusion coefficient has a step size embedded in it, right? And if I think in terms of using the temperature for optimization, because that will be used essentially for optimization, it's like I fix beta, which is the inverse temperature, and hopefully it's understood what I'm saying, with a step size. And we know this is not good, this is not working. So I wonder if you have any comment about that, because I see that we try to hide the wrong scaling that comes from the initial idea into the diffusion coefficient, but then we remove one important parameter for this whole approximation, which is beta. It's a free parameter.
I cannot comment on this really, because this is all existing works. It's not over. So I cannot really tell you here what exactly is the rationale here behind the scaling.
Okay, I'm saying that just to conclude it, because beta is a high parameter for these Langevin type of equations, and we use it many times for different values to see how we get optimally the convergence to explore the space. So just that, okay.
So it depends on the parameterization, but I think your piece is this gamma to alpha minus 1/alpha or 1 over that. And indeed, that's why in practice in SGD, they don't take gamma all the way to 0. They make it small enough that you will still see some nice convergence, but not all the way to 0, because otherwise your process also doesn't move a lot. You have a very hard time leaving.
Now I understand your gamma, so the learning rate is what I think you call beta, the temperature, which would be the learning rate. And actually, if you add choose the learning rate adaptively, that goes to 0, then you can get convergence to the optimum. But this is not what you want because of generalization.
Yeah. No, not exactly. But we can discuss later on that. That beta is an additional parameter and is used for optimization, right? Because this is what we want to do here. We want to solve optimization problem, not sampling. So there is a difference. Yes.
Okay, so this now motivates this model of homogenized stochastic gradient descent. And so again, so this model is not, we did not invent this, we did not invent this model of homogenized stochastic gradient descent. So this was proposed previously in the literature. So what we did, we studied the distributional properties of homogenized stochastic gradient descent. And in particular, we connected it with heavy weights, and we showed that it has this heavy weight property. Yeah, but the basic idea is to approximate stochastic gradient by a diffusive stochastic differential equation, but without assuming that the covariance is constant, but keeping the state dependency in the covariance matrix. And as I've said, gradient norms will be locally Gaussian, but globally non-Gaussian and heavy weight. And if you also assume the assumption of a quadratic loss, then you will get a very tractable model. Yeah? And in particular, what we have shown is that we can get explicit tail index bounds in these models. And also, under some conditions, Wasserstein convergence guarantees to equilibrium distribution. And in the one-dimensional case, so in the non-Gaussian alpha stable model, the stationary distribution will be an alpha stable distribution. In our case, the stationary distribution will be skewed for the student T distribution. As in the one-dimensional case, in the high-dimensional case, we cannot say anything about the distribution exactly, but this skew student T distribution will still be a lower bound in convex order for all the marginal distributions. And convex, a lower bound in convex order means that the actual distribution will be more heavy-tailed than our lower bound. Yeah, so this is nice because it still characterizes the heavy-tailedness of the distribution. And as I said, we simplify the setting by assuming a quadratic loss function, but also with quadratic regularization. So in statistics, we would call it a rich regression. So we are estimating rich regression parameters by stochastic gradient descent. And our analysis also takes place conditional on the training data. So we don't have to impose any distributional assumptions on the training data for our results to hold true, but in order to use the existing results that guarantee that it is a good approximation to stochastic gradient descent, you may need some additional assumptions on A and B. But once you accept the approximation by homogenized stochastic gradient descent, everything is conditional on the training data. And for training data, the feature vectors AI, we put them in a matrix A row by row, and our labels, we put them in a vector B. So up from now on, everything will be in this matrix vector notation given by A and B. And of course, the recursion for stochastic gradient descent now also simplifies. And here, this sampling is represented here by this basis vectors EI chosen randomly. And what we do, so as I've mentioned, there are different ways of sampling. Here, what we do is what is called random sample stochastic gradient descent, which means we are iterating through our training data multiple times, and we are sampling uniformly randomly with replacement. Yeah, this is just the easiest case to treat theoretically, and we are also allowing batch size larger than 1. So we are treating the random sample mini batch case with B larger than batch. And now, one crucial ingredient of this homogenized stochastic gradient descent approximation is that you have to simplify the covariance matrix somehow. So this is the first line is still the exact expression for the covariance matrix for stochastic gradient descent. It's difficult to work directly with this, and here this uses an approximation that is non-obvious. This approximation. And it was introduced in a paper by Mori and others using some heuristic arguments, using properties of high-dimensional Euclidean scale. And covariance matrix is approximated by basically the loss function times the Hessian matrix of the loss function. And luckily, there are some rigorous results to back up that this approximation actually works. And this is now given in a paper by Paquette and others, where they introduced and they actually coined this name of homogenized stochastic gradient descent, which is now SDE approximation of stochastic gradient, and using in addition this decoupling approximation here for the covariance surrogates. And they also give results that under certain assumptions now on the data generating distribution of A and B, that and give guarantees like this, that in high dimensions, so as dimension D gets larger, that this SDE approximates well the behavior of actual stochastic gradient and this. And up to now, this was all coming from the existing literature. And what we did now is that we use this homogenized stochastic gradient descent and look at the distributional properties in the case where loss is given by penalized what that is. And well, if you use a quadratic loss function, of course, here f now gradient of f will be linear. The loss will be quadratic, the Hessian will be constant. So here we'll see a quadratic function, and here we see a linear function of x. And then you can further simplify this by using a singular value decomposition of your data matrix A. Yeah, so the idea is somehow you have a very high dimensional SDE, and you try to decouple the components of this SDE. And you do this by using the reduced singular value decomposition. So the singular value decomposition where we throw away all the zero singular values and only keep the strictly positive singular values. So R is the rank of A, and lambda contains now the R singular values, which are strictly larger than zero. And furthermore, we will have to distinguish two cases. And the first case is the underparameterized case. Now, this is the case typically, but not exactly, but typically where D is smaller than N. So where the equation AX equals B has no exact solution, which means that no matter how well we train our model, it will never be able to fit exactly your training data, and the loss will always be strictly larger than zero. But we can also treat the overparameterized case when we have additional regularization. So in the overparameterized case, by this I mean that now AX equals 0, AX equals B has an exact solution. So in principle, our model is able to perfectly interpolate the training data. And usually you do not want this because then your model will not be able to generalize well. So in this case, we are assuming addition that there is regularization. So delta is strictly larger than 0. In the first case, we could have regularization, but it's not necessary. Now, these are the two cases we can treat here. And now, as I've told you, the idea of using the singular value decomposition is to decouple this SDE. And we do this by transforming now the vector x to an r-dimensional vector y here, using the singular value decomposition, and in particular shifting it such that now the minimum of the loss function will be located at 0. And now you can rewrite this equation like this. And if you write it component by component, then you get this. And now this is the ith component here. And now if you look at the drift part, the drift parts now have been completely decoupled, because here in the drift of the ith component, you see only the ith component of the process. You also see here now the singular value appearing, but the components are still coupled to the diffusion component, because in the diffusion component, you have here this sum here over the squares of all the components. So this still couples the whole process.
What's alpha? Okay.
So alpha is up there. Alpha is coming from the regularization. So if delta is 0, then alpha is 0. But if you have some regularization, you also have some pull away from the global minimum. And beta is also interesting because beta distinguishes between the underparameterized case. In the underparameterized case, beta is strictly larger than 0, and in the overparameterized case, equal to 0. You see that we will have to treat these two cases a bit different, because in the second case, the beta here will vanish.
And Martin, quickly, sorry if I missed that. Do I have any coercivity condition then for this system in order to control moments when t goes to infinity?
Will come in a minute.
Okay.
Okay, thanks. Okay, so now I already come to our results now on the distributional properties, and I will present first the results, and then I will say something on the proof. Now, so the first result is now an upper bound on the asymptotic tail index. So we can bound the asymptotic tail index from above by this quantity here, depending on the various parameters here, sample size n, batch size b, learning rate gamma, and also on the leading singular value lambda1 of the data matrix A. And in particular, an upper bound is nice because it tells us that the tails have to be at least as heavy as this upper bound on the tail index tells you. And as I've said to you, we cannot show that in any case there will be a stationary distribution, but if it exists, then it must be heavy using this upper bound. And the second result gives a matching lower bound. So here now we have a condition on the learning rate. The learning rate must not be too large here. So if the learning rate is smaller than this bound here, then we have a lower bound. And the first part of the lower bound is upper bound. But now we're subtracting something, so the lower bound is.
So what's the
upper bound as it should be? Yeah.
what the order of the learning rate is like n squared?
Sorry, where?
What's the order of the learning rate like? So like
In which parameter?
in n or yeah, n squared is like a very large rate.
Here is n squared.
Yes, n squared is like very large.
But there's also delta here. So delta can be 0. If there's no regularization, delta will be 0. And also lambda1, I mean, somehow depending now on.
It's something like n by d or something.
So some dependency on n and d is also hidden in lambda1. So because, for example, typical assumption would be that your feature vectors A are coming from Gaussian distribution, i.e. Gaussian, and then you can apply random matrix theory, and then it will tell you that the singular value, for example, will behave like a square root of d in case in dimension, and also square root of n. And you have to decide for some regime where n and d goes to infinity at the same time, and then so there's also something hidden here in lambda1.
But that's not bad. If the upper bound is big for your step size. Well, you have more freedom to choose.
Yeah. So yeah. Okay. And in this case, we also have this lower bound here. And now, of course, you can look now, having these bounds, you can look at the dependency on the various meta parameters of your optimization procedure. And for example, you see that both bounds, they behave in the same way. So they are increasing in regularization delta. This means if regularization is stronger, then the tails will be lighter. And they're also increasing in the batch size. So the same thing, if the batch size is larger, then tails will be lighter and behave more Gaussian, which makes a lot of sense. But they are decreasing in the learning rate. So if you increase your learning rate, then it's heavier. They're also decreasing in the singular value lambda1, which kind of corresponds to the curvature of the loss function at the local minimum, and which means if the curvature is larger, lambda will be larger. It will also be heavy, which is also nice because this heavier tails means there are more extreme movements, which allows you to get out of your local minimum. And in fact, this qualitative analysis, this has also been given in this paper by Gürbüz-Balaban, where they studied discrete recursion. This agrees completely with their observation. So qualitatively, our tail-bound behaves exactly the same way as their result of the tail index. The difference is that they obtain under some additional assumption on the data on the isotropic Gaussian distribution, and their result is not quantitative. So they obtain these qualitative results, but they cannot give a quantitative expression for the tail index, whereas we give at least low and upper in a quantitative way. And except one thing, that here we don't have a dependency on dimension, whereas in their paper they have a dependency of the dimension B. But again, this can be explained when you now put additional assumption on the data generating mechanism, when you use this assumption of isotropic Gaussian distribution, then you can apply random matrix theory, you can apply results from the Wishart ensemble, and then you will see that lambda1 will scale with square root d, and then also our index estimate becomes decreasing in dimension. So it actually, there's no contradiction or no difference actually qualitatively between our results. Okay, now let me briefly speak about the strategy for the proof of the upper bound, and also in the case where beta is strictly larger than 0, so the underparameters case. So we do another scaling of the SDE, and then it will look like this here, and still coupled here to the diffusion coefficient. And now what we do is we define a second process, set head, where we throw away here everything in the sum except for the ith component. And this, of course, now decouples the process, and we get a one-dimensional SDE, which is very nice. So it has a linear drift, it has a quadratic diffusion coefficient, and this is known as a so-called Pearson diffusion. And the nice thing is that we can still learn something about the coupled system from this SDE here, because the only thing we changed is we made the diffusion coefficient strictly smaller. And for such SDEs where you are shrinking the diffusion coefficients, there are comparison principles by Buschendorf and others. And here in this case, this will be a lower bound in convex stochastic variables. And you're only reducing the variability of your noise, and this will also only reduce the variability of the marginal distributions. And these Pearson diffusions, they are well studied. So you know the behavior of moments, you know stationary distributions. And in this case, the stationary distribution is a skew student T distribution, or Pearson type 4 distribution. And just look like this here, but the throughput parameter for us is right in the symmetric place where mu is 0 is the degree of freedom parameter eta. Because this controls now the existence of moments and the TMLW02. So moments will be finite if and only if P is smaller than the degree of freedom parameter. And now, as I've said, this is a lower bound in convex order. So this means that for any convex function G here, expectation of G of the component of the original process will be lower bounded by expectation of G of the Pearson diffusion. And in particular, this implies an ordering of moments. And as soon as you have an ordering of moments, you can compare the tail indices of the two processes. And in the overparameters case where beta is 0, the proof is analogous, but we have to scale a bit different. And instead of a type 4 distribution, you have a type 5 Pearson distribution as a lower bound. Okay, so and now final result, again, if the learning rate is small enough, so if the learning rate here satisfies this upper bound, then this nonlinear equation rate rho will have a unique positive proof rho star, and under this condition, we will get convergence in two Wasserstein distances. In this case, we can actually show that there is a unique invariant distribution among the conversion for Wasserstein distance at exponential rate given by this number rho star. Okay, so this was the theoretical part, and now let me conclude by showing you some experiments where we validated the tail bound. So this is on 3 different data sets. So first is ridge regression on a synthetic data set, and the other 2 are random feature models of different dimension on a handwriting data set on MNIST data. And here you see the complementary cumulative distribution function in double logarithmic scale for the empirical distribution in orange, and the 2 upper bound, the 2 bounds in green and blue. And you can see that these are sandwiched nicely between the lower and the upper bound. And the second thing that we looked at is kind of because our results suggest that as a stationary distribution, at least for a one-dimensional marginals, that we should not use an alpha stable distribution, but instead a skew student T distribution. Or here we even drop the skewness, so we just look at symmetric student T distribution, and we fit it now to the empirical data that we get from stochastic gradient descent. And here you see that in the top row, you see now two plots for student T distribution, which agree almost perfectly. And in the second row, you see now two plots of a fit of an alpha stable distribution, which again are not too bad, but clearly with much more deviation than the student T distribution. And in fact, if you do some statistical test here, like a Kolmogorov-Smirnov test, then alpha stable distribution is rejected in all three cases, whereas student T distribution cannot be rejected. Okay, so with this, I'm at the end of my talk. Let me sum up once again. So I have proposed here to use homogenized stochastic gradient descent as a model, which uses locally Gaussian gradient noise, but globally leads to non-Gaussian and heavy phase parameter distribution. We were able to give explicit upper and lower asymptotic index bound in terms of the hyperparameters of stochastic gradient descent, at least in the ridge regression setting. And we have also obtained a skew student T distribution the convex or a lower bound for the marginal, and it seems to be a good approximation of the work. And numerical experiments are also different of theoretical figure. Thank you very much for your attention.
Any questions? Yes.
So I just like wanted to understand this upper and lower bound thing a bit more. Can you go back to this slide?
This here?
Yes. So this is the lower bound on the tail index, right? This is the.
Yeah.
Like, yeah, so I just don't intuitively get it. Like, what does it?
So you said this upper bound. Where is low?
Say like theta of
Which one?
the yeah, eta.
You for eta. This one.
Yeah.
So intuitively, I can also not say much about it. I can also say that the lower bound is much easier to obtain than the upper bound, because for the upper bound you need this new idea of this convex order lower bound. For the lower bound, you just apply existing results using the Lyapunov function for SDEs, and this immediately pops out. Yeah. So.
And the other question is like stupid one, but like, is the delta is a necessity there, or you can make like without regularization and also over parameterize?
In the over-parameterized case, not. In the over-parameterized case, we can not leave out the delta, because what happens, you can get stuck at the local minimum. So, okay, basically, in high dimension, still fine, because you will typically, you will never, due to the noise, you will never arrive exactly at the global minimum. Yeah, because when you add the global minimum, gradient is zero, but also noise is zero. So then you will get stuck. But if you want to work with this trick where you project down to a one-dimensional distribution, then this no longer works, because then you will always at some point reach your local minimum, noise will vanish, gradient will vanish, and you are stuck at it.
Sorry, so but this is a least square case. So there is just one, like okay, so there are like three minima, right? Like it can be many minima, but the values are same. So it can be like,
yeah, so there can be many minima, and at any of these minimas you get stuck, because both gradient and noise vanish. No?
yeah. So for example, SGD or gradient descent, they probably goes to the minima with like minimum L2 norm. So you don't, like if you run SGD on over parameter least square, you don't need to add regularization. You can show that like in few lines that it will go to the minimum norm solution. So so I'm just like wondering that this homogenized SGD does not have these properties. Like
if you leave out the regularization, it will Now, okay, so the other problem is that here. Yeah, so here, so X is the original SGD, and here we are projecting down to just the R components corresponding to the non-vanishing singular values. And here you're using some information. You cannot go back. You cannot invert this transformation, which for us is good enough because we're interested in the tail behavior. So we just need like one direction where we observe heavy tail behavior, and it's good enough to make a statement on the full process. But now, if you're interested in other properties, this might not tell you so much because you cannot go back to the original. So if you want to know exactly the trajectory of stochastic gradient descent, then this information is kind of lost here in this project. For some properties, it's good enough, but for other properties, it's probably not the right thing to do.
Any other questions? I think I have similar concerns as Sotirio. So can you really say that this SDE approximates SGD if you have the wrong noise scaling? Because right now it seems to me that the argument looks like this, that you have this step size gamma in SGD, and then near the noise you have gamma, so you split it like a square root of gamma times square root of gamma, and then you would argue that, okay, if the discretization parameter goes to 0, then you have the SD in the limit, but now, okay, so one of these square roots will go to 0, but the other is fixed, and then this other square root of gamma appears in the noise, which seems a little bit non-rigorous.
Well, they never really take eta or gamma to 0. So in reality, so like for example, in Langevin, you have a discretization parameter and the temperature, and here you have a single parameter. So somehow you don't want very small or very large eta. You should find some balance.
Yeah, for the practical implementation, yes.
Yeah,
But
for the
there is a
theoretical
result where you get the limit.
Yeah, no,
Yes, and there you say approximate, you know, the continuous dynamics, which is an SD. Do I have the right scaling? If you don't hit the SD. Right? This is what we're saying.
Because the SD,
so it's okay.
I mean, yes,
The SD
I
would
agree.
be a good approximation for SGD exactly for very small.
There's a lot
values
of
of
hand
gamma,
waving,
right?
but I mean, Michael Jordan and many other people already do it.
You do it, so we should do it as well.
I'm not sure. I mean,
Cut the corners
think
a little bit and get
Martin
there.
was just analyzing after the hand waving. Okay.
So fair enough.
Yeah, so here I have said there are two different scales. So this is from the original, so from the older paper of Hoffman and Blei, when he sent a learning rate to 0. But later in the homogenized stochastic gradient descent, here the scaling is basically so now learning rate is not that. Learning rate is constant, but now 1 unit of time corresponds to n steps in stochastic gradient descent. And the asymptotic regime is that n and d go to infinity at the same time. Yeah. So learning rate is non-dimensional. Yeah. Sample size gets large and dimension gets large at the same time. This is more recent work, and they are really doing something more smarter. Yeah.
If sample size and the dimension will become large, then eventually the learning rate will go to 0, like in many of these works at least, because they have to be like eta times d times n should be some constant or something. So if d goes to infinity,
then so the learning rate is kept constant.
So there is another procedure that we have in mind. Yes. So the learning rate for us, let's say in the drift parameter, controls essentially controls dt. You see what I mean? So if you were to change scales and somehow make gamma appear in the drift coefficient, then what you expect to see from dw, the square root of gamma will appear because this is the right scaling. Right, in order to get the approximation then correctly, but okay, so maybe this is another approach, and that's why I was wondering, and sorry I didn't understand because you talked finally about the invariant measure there in this case, but sorry I missed that. Did you mean the invariant measure when you reduce to the one-dimensional, or for the multi-dimensional?
Multi-dimensional.
For the multi-dimensional,
Multi-dimensional, so if.
through the convex order, you will be able to, no, I didn't get that.
For the convex order result holds for all the marginals, even at finite.
Yes, yes, yes.
Holds, even if there is no stationary distribution or if we cannot show there's a stationary distribution, still we have this convex order bound at all the marginals. But then if learning rate is small enough, we have this stronger result that there is a, sorry, I skipped it. Yeah, that there is a invariant distribution in the multi-dimensional case, and then for any one-dimensional marginal skew student T is going to be a lower one.
Okay, yes, okay, which is a good result, yes, that one.
Okay, let's thank the speaker again.